Okay, well, we talked about, this notion of pull-up and pull-down networks and creating connections where we want them, and we talked about what happens when they're both on. This red line, we want to avoid that. And this one where they're both off, we're going to talk about memories in a couple weeks, so we'll come back to that one. So here are the complements, right? So an N-channel device conducts when its input is high, the gate is high. The P-channel device conducts when its input is low, so I can put them together in an inverter. These are complementary circuits. When one conducts, the other doesn't. Okay. Here's another. So series connections of NFETs, what's the complementary circuit? Is parallel connections of PFETs. Okay. So when A and B are both high, I get a conduction between the top node and the bottom node in this series connection. Okay. When either A or B are low, I have no path from the top to the bottom in the NFETs, but I have at least one path in the top to bottom connection of the parallel circuit of PFETs. So think of all the possible combinations of A and B, low and high, and you'll discover that one of these paths conducts and the other one doesn't, and whatever the combination is. And similarly, parallel NFETs and series PFETs are complementary. And now we have the secret to how to build CMOS logic gates. Remember, you used to come in and the map of Africa was pulled down over the blackboard, in math class, and you always wondered why the math teacher had a sudden fondness for Africa, and the answer is, well, her pop quiz was underneath the map, right? So boom, pull up the map and there would be the quiz. That's what it was when I was young. Okay, so here's a pop quiz. Here's a circuit. Can you recognize the pull-down path? That's where all the NFETs are. So that's below this output node here, which is the node with the arrow. This is the output node. Can you recognize the pull-up path? It's a parallel connection of PFETs. So we have series NFETs and parallel PFETs. A and B are connected to the gates of each. So this is actually a connection from B both to the gate of this guy and then up here to the gate of that guy. Let's figure out what this gate is. So when A and B are both low, so first of all, how many different combinations of A and B are there? There's two inputs, so we have A and B. So I'm going to write my little functional specification, and I'm going to do it in the form of a truth table, where I'm going to list all the possible combinations of A and B, all the possible binary combinations of A and B. So when A and B are both 0, what's on and what's off? Yes? They're both on. So the PFETs are on. What about the NFETs? They're both off. So what connection do we have between the output node and one of the power supplies? We have a pull-up path, so we expect the output to be 1. How about when A is 0 and B is 1? Yes?
When A is 0, the PFET on the left is on.
Right, so this guy is on.
Yeah, that guy is on. The other PFET is off.
Right. And what about a pull-down path?
There is no pull-down.
There is no pull-down path. Right, so again we have high... And, I'm sorry?
There should be 1.
No pull-down path, we had a pull-up path. Thank you. Same thing here, and then what happens when they're both 1? Both PFETs are off, and the two NFETs are now conducting, so I actually get a pull-down path. This gate has a name, okay? It's called a NAND gate, not of AND. Okay? And you can look at this and you say, oh, okay, that's pretty good. Here's an actual picture of a mask layout. The dimensions of this thing, I've just sort of done it symbolically in terms of this basic, smallest dimension, which you call lambda. And lambda in a modern process is a couple, in this case, 25 nanometers. So this gate isn't very big. On a slightly older process, I sort of go through the mechanics of figuring out how much area this is, and on a 12-inch wafer, how many of these can I build and for how much money. And you can sort of see down here when I'm all done, the cost of one of these two input NAND gates is somewhere around 100 nanocents. And that number is probably half that cost today. Okay, so you can, for $1, you can buy, hundreds of millions of devices. right? And Intel then sells them to you for $500, but that's, that's called profit. They have to pay for a lot of things, but they clearly have a little bit of margin to work with. All right, everybody sort of see what's happening here, right? How about this device? What's the analysis you could do? Well, you just go through the truth table here, and this is something you should work through. You should be able to figure out, for each of A and B being 0 or 1, you should be able to figure out that and come up with that as the truth table. It's called a NOR gate. Let me ask you about a different logic function. How about 0, 0, 0, 1? This would be AND. This is true when both A and B are 1. Can I build a little pull-up and pull-down networks that implement that? In other words, does this recipe work? So I have a little recipe for constructing a pull-down path, constructing a pull-down path and a complementary pull-up path. What do you think? Can I build a set of pull-up and pull-downs that implement that? Well, let me run a couple ideas behind you. When the inputs are all 0, what can you tell me about the P FETs and the N FETs? When all the inputs are 0, are the P FETs on or off? They're on. So if there's any sort of network that's, will make a conducting path between the output node and the power supply, the high power supply, okay, it's bound to be turned on when these guys are all 0. So in a CMOS gate that has, this sort of one pull-up network and one pull-down network, if all the inputs are 0, what do you expect the output of the CMOS gate to be? Well, it has an active pull-up, so it must be 1. So, oops. So a CMOS gate will always produce a 1 in the case that all the inputs are 0. How about when all the inputs are 1, what will a CMOS gate produce? For sort of the symmetric reason. It doesn't matter what the network you've designed is, okay? So it turns out that CMOS, so this, can you implement this in a single CMOS gate? No, you can't. There's just something about this truth table. So we can't do this for every possible truth table. We can't build a single CMOS gate for every possible truth table. We can only build it for certain types of truth tables, the ones that describe inverting logic. Logic where rising inputs lead to falling outputs. And if you think a little bit about that, as an input rises, it's turning on N FETs and turning off P FETs. And if you're turning off P FETs and turning on N FETs, the only thing that can possibly happen, if anything happens, if something changes, if we finally get a path, is that we turn off a pull-up path and turn on a pull-down path, and the gate will fall. Rising inputs lead to falling outputs. Yes?
Why can't you switch the N FETs?
Why can't I put P FETs at the bottom and N FETs at the top, and then I could do anything I wanted to? That's a great question. The reason we can't do that is that involves an explanation about how these devices work that is far too complicated for us to go into. So remember the set of rules where we only use P FETs in the pull-up and N FETs in the pull-down? That was the set of rules that allowed us to treat these things as voltage-controlled switches. If we disobey those rules, these things no longer behave like voltage-controlled switches, and they do things that actually make what you're trying to propose, which is to use the negating switches in the pull-down path, the P FETs in the pull-down path. They won't behave the way you'd like. Okay, they don't behave as voltage-controlled switches anymore. Yes, sir? Can we just put a NAND with an inverter? So the way we do this sort of implementation is we build a NAND gate and follow it by an inverter. Right, so it's a little bit slower. So positive logic, non-inverting logic instead of inverting logic is basically slightly slower in CMOS than. And in the next couple of things, we'll learn how to do everything with inverting logic gates, as it turns out.